Welcome you all to today's session, children. In the last video, we have studied about the classification of elements and the attempts which were tried by scientists to classify elements, and also we have studied how to name the element with atomic number greater than 100. In today's class, let us learn about electronic configuration, and we will study about S block, P block, D and F block elements. Now to discuss about the electronic configuration of elements in a period. Now we know that the period indicates the value of n for the outermost or valence shell. In other words, successive period in the periodic table is associated with the filling of the next higher principal energy level. That is, n is equal to 1 first period, n is equal to 2 second period, like that. It can be seen that the number of electrons in each period is twice the number of atomic orbital available in the energy level that is being filled. The first period, n is equal to 1, starts with the filling of the lowest level, that is 1s, and therefore has 2 elements, hydrogen and helium, with the electronic configuration of 1s1, and for helium 1s2. That is the filling of the first shell where K shell is completed. The second period, n is equal to 2, starts with lithium. You can see in the periodic table, the second period starts with lithium, and the third electron enters the 2s orbital, that is atomic number 3. So the electronic configuration is 1s2, 2s1. So the third electron enters the 2s orbital. The next element, beryllium, has 4 electrons, and its electronic configuration is 1s2, 2s2. Starting from the next element, boron, the 2p orbital are filled with electrons when the L shell is completed at neon 2s2, 2p6. So we can see that neon has got the electronic configuration of 2s2, 2p6. Thus there are 8 elements in the second period. The third period with n is equal to 3 begins at sodium, and the added electron enters the 3s orbital for sodium, atomic number 11. So you can see that the outermost electron is present in the 3s orbital. When you write the electronic configuration, 1s2, 2s2, 2p6, 3s1. Successive filling of 3s and 3p orbital give rise to the third period of 8 elements from sodium to argon. The fourth period, n is equal to 4, starts at potassium, and the added electron fill up the 4s orbital. We can note that before the 4p orbital is filled, filling up of the 3d orbital becomes energetically favorable, and we come across the so-called 3d transition series of elements. That is, the 3D series starts from scandium, atomic number 21, which has the electronic configuration of 3d1, 4s2. The 3d orbital are filled at zinc, atomic number 30, with electronic configuration of 3d10, 4s2. The fourth period at krypton, with the filling up of the 4p orbital. Altogether, we have 18 elements in the fourth period. So you can refer to the table. Fourth period has got 18 elements. The fifth period starts as n is equal to 5, beginning with rubidium, is similar to that of the fourth period and contains the 4D transition series starting at yttrium with atomic number 39. This period ends at xenon with the filling up of the 5p orbital. And the sixth period, where n is equal to 6, contains 32 elements, and successive electron enter the 6s, 4f, 5d and 6p orbital. That is according to the increasing order of energy. In the order, filling up of the 4s orbital begin with cerium Z is equal to 58 and ends at lutetium, that is Z is equal to 71, to give the 4f inner transition series, which is called lanthanoid series. So you can see at the bottom, which are called as lanthanoid series. And the 7th period, n is equal to 7, is similar to the 6th period with the successive filling up of 7s, 5f, 6d and 7p orbital, and indicates most of the man-made radioactive elements. This period will end at the element with atomic number 118, which should belong to the noble gas family. Filling up of 5f orbital after actinium, that is atomic number 89, give the 5f inner transition series known as the actinoid series. The 4f and 5f inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. When we compare the electronic configuration according to the group, that is group-wise electronic configuration, elements in the same vertical column or group have similar valence shell electronic configuration, same number of electrons in the outermost shell and similar properties. For example, let us take the elements from lithium, which is having atomic number 3 with the electronic configuration 1s2, 2s1. And next element sodium, which has the electronic configuration of 1s2, 2s2, 2p6, 3s1, that is with the 11 as atomic number. And when we take the next element potassium, again 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So we can see that all these elements have similar electronic configuration with one electron in the s suborbital of the outermost shell. Thus, it can be seen that properties of the elements have periodic dependence upon its atomic number and not on its relative atomic mass. Now, let us see about the classification as S, P, D and F block. We can classify the elements into 4 blocks called S block, P block, D block and F block, depending on the type of atomic orbital that are being filled with electron. We notice 2 exceptions to this categorization. Strictly, helium belongs to the S block, but its positioning in the P block along with the other group 18 element is justified because it has a completely filled valence shell. That is 1s2, its electronic configuration, first energy level, S suborbital with the 2 electron completed. So it is a completely filled configuration like noble gas, and as a result exhibit the properties, characteristics of other noble gases. The other exception is hydrogen. It has only one s electron and hence can be placed in group 1 along with the alkali metal. It can also gain an electron to achieve a noble gas arrangement, and hence it can behave similar to group 17, that is like halogen. Because it is a special case, we shall place hydrogen separately at the top of the periodic table. Now let us see the properties of the elements of S block. So the S block elements, the element of group 1, which are called as alkali metals, and group 2 alkaline earth metal. You can see at the left side corner alkali metal and alkaline earth metal, which and they have the NS2, NS1 and and NS2 outermost electronic configuration. They belong to the S block. They are all reactive metals with low ionization enthalpy. They lose the outermost electron readily to form +1 ion, and also the second group element, they lose the outermost electron, 2 electron, to form +2 ions. So the metallic character and the reactivity increases as we go down the group. Because of high reactivity, they are never found pure in nature. The compounds of the S block element, with the exception of those of lithium and beryllium, are predominantly they are ionic in nature. Now let us see to the elements of P block. The P block elements comprise those belonging to group 13 to group 18. On the right hand side, the elements from group 13 to group 18, and these together with the S block elements are called as representative elements, or they are the main group element. The outermost electronic configuration varies from NS2-NP1 to NS2-NP6 in each period. At the end of each period is a noble gas element with a closed valency shell with the configuration of NS2-NP6. All the orbitals in the valency shell of the noble gases are completely filled. So they are called as inert gases. They have completely filled electrons, and it is very difficult to alter the stable arrangement by the addition or removal of the electron. The noble gases thus exhibit very low chemical reactivity. Preceding the noble gas family are two chemically important groups of non-metals. They are halogens. Just to the left of the noble gases, we have got halogens which belong to the group 17, and the chalcogens, that is group 16. These two groups of elements have highly negative electron gain enthalpy and readily add 1 or 2 electrons respectively to attain the noble gas configuration. The non-metallic character increases as we move from left to right of the periodic table, and metallic character increases as we go down the group. Now let us see the elements of group D, the D block elements. These are the elements of group 3 to 12. Group 3 to 12 are called D block, which are placed in the center of the periodic table. These are characterized by the filling of inner d orbital by electron and are therefore referred to as D block elements. These elements have the general outer electronic configuration of n-1d 1 to 10, ns 0 to 2. They are all metals. They mostly form colored ions, exhibit variable valency. They are paramagnetic in nature, and they are used as catalysts. However, zinc, cadmium and mercury, which have the electronic configuration n-1d10 ns2, they do not show most of the properties of transition element. In a way, transition metals form a bridge between the chemically active metals of S block element and the less active elements of group 13 and 14. So you can see the transition elements form a bridge between the S block and the P block element, and their familiar name as transition elements. And the F block elements, inner transition elements. F block elements are also called as inner transition elements. The two rows of elements at the bottom of the periodic table. So you can see at the bottom there are two rows of elements which are called as lanthanoids and actinoids. Lanthanoids, that is Ce is equal to 58 to Lu is equal to 71, and actinoids with atomic number Z equal to thorium, that is Dh atomic number 90 to Lr, that is atomic number 103. They are characterized by the outer electronic configuration of n-2 F 1 to 14, n-1 D 0 to 1 and ns2. This is the general electronic configuration. The last electron added to each element is filled in the f orbital. So only they are called as f block element. These two series of elements are hence called inner transition elements, f block elements. They are all metals. Within each series, the properties of the elements are quite similar. The chemistry of the early actinoids is more complicated than the corresponding lanthanoids due to the large number of oxidation states possible for these actinoid elements. Actinoid elements are radioactive. Many of the actinoid elements have been made only in nanogram quantities or even less by nuclear reactions, and their chemistry is not fully studied. The elements after uranium are called transuranium elements. Now let us see about the characters of these elements as metals, non-metals and metalloids. In addition to displaying the classification of element into S, P, D and F block elements, these elements can be divided into metals and non-metals. Metals comprise more than 78% of all known elements and appear on the left side of the periodic table. Metals are usually solids at room temperature. Mercury is an exception. Gallium and cesium also have very low melting point. Metals usually have high melting and boiling point. They are good conductors of heat and electricity. They are malleable and ductile. In contrast, non-metals are located at the top right side of the periodic table. In fact, in a horizontal row, the property of elements change from metallic on the left to non-metallic on the right. That is, on moving from left to right of the periodic table, metallic character increases and non-metallic character increases. Non-metals are usually solids or gases at room temperature with low melting and boiling point. They are poor conductors of heat and electricity. Most non-metallic solids are brittle and are neither malleable nor ductile. The elements become more metallic as we go down a group. The non-metallic character increases as one goes from left to right across the period. The change from metallic to non-metal character is not abrupt. The elements silicon, germanium, arsenic, antimony and tellurium, you can see in the periodic table on the right hand side. These are all metalloids. That is, we can see that bordering this line running diagonally across the periodic table shows properties that are characteristics of both metals and non-metal, and these elements are called semi-metals or metalloids. So, in the next session of the video, we will be reading about atomic radius and the related properties.